We did very long electron structures, basically relating the periodic table arrangement and how each of the atoms are arranged in a bunch of different orbitals. So, if you missed Friday's lesson and didn't watch the video, some of this lesson will not make any sense. So, we'll try to stay with it. Can't do the whole thing over again, but I'll try to explain as best I can. So, basically going through the periodic table, we can basically assign each of the different chunks of the table. It corresponds to different shapes of where electrons can be. Now, electrons fill up the table in the order of the periodic table, basically going along atomic number, basically one at a time. So we get to practice. We're going to do the electron notation for aluminum. So we're going to start with aluminum. What number is aluminum on the big table? Everyone's looking at their periodic table and found aluminum is number what? 13. Good. So we only have to deal with 13. That's not that bad. It's not a big one. I didn't grab lead or anything unnecessary. So we're going to do aluminum, which has 13 electrons. Right? There's 13 electrons in it. And so basically what I want to look at is how do I arrange these 13 electrons? We go basically through the table. So this is a little bit of recap. Those of you that were here on Friday can already write this one. They already know how. So we start with the top of the rows. We have hydrogen and helium, those first two elements. They are called the 1s orbitals. And so we start with 1s2. So those two are the first chunk. They're called 1s2 orbitals. Then we go down to the next two, and that's our 2s2 orbitals. So we've covered the first four elements. We've gotten up to our lovely beryllium in this case. So we've covered those two. And if you notice at the table, after beryllium, we take this huge jump over to where boron, carbon, and nitrogen are. That jump is because they're in a different shaped orbital. And that shape is called p, and there are 6 in that line. So this is the 2p6 orbital. So this is a real continuation from Friday's lesson. So I see some big eyes, and so we're trying to catch up. So now we've covered all the way to the end of row 2, which is neon, which is number 10, and we have done 2 plus 2 plus 6, which is 10. We've covered these 10 electrons so far. Then we can go to the next row. We have the third row down, that's 3s, and there's 2 of those, 3s2. And now we've gotten to the magnesium chunk, and aluminum's one more. And since aluminum's right below that boron, carbon, nitrogen chunk, this is also the p-style chunk, and so there's going to be 3p1 electrons. So basically, to point this out, so this is finished. This is how aluminum works. And so if we add up each of these, 2 plus 2 plus 6 plus 2 plus 1, that adds up to the 13 in the total number of electrons. Now, to save you guys writing all of these, aluminum's not bad. But if we get into the heavy elements like tin, like mercury, like any of these really big elements that have 50 or 80 electrons, this is going to get into a massive thing. So what we're going to introduce is a core notation. Using noble gases is the base. So in this case, I'm going to show this base. Oops, pen back on. This chunk here, what element does this chunk correspond to? And you can do this just by adding up the tops. If you add up the tops, what do we get to in this chunk? 10, right? So what element is 10? It's neon, right? So this chunk is the same as neon. And so what we can do is we can use noble gases as our base. And so what we're going to write aluminum as is we're going to write aluminum as neon plus what's left. So the way we write that is going to be, I'm going to write this equals as it's the same thing. It's going to be written as neon in square brackets to basically say all the electrons neon has plus extras. And so the extras are just this chunk here. And so those are what comes next. And so this is going to be 3s2 and 3p1. So aluminum is neon plus 3s2 plus 3p1. Neon plus 3 is neon. Is aluminum. Aluminum is neon plus 3. And that's just a way for us to save writing so much repetition in these kinds of structures. And so we can be a little bit less full-page nonsense. In the next table, we're going to compress these. These are the full notations as written, all of the electrons in these particular elements. And so we can write what comes back. So we're looking for, so as I write my hint here, look for last full p orbital. That looks like something p6. So if you see a p6, that's our last full orbital. So let's look at the first one. We got a sulfur notation. Which one is my last p6 that's full?
Why does it say 1s1?
Where? Oh, that's weird. Yeah, it does. That's not right. They 100% are 1s2s. That's weird. Good noticing. So, for those of you not doing, all of those should be 2s. Absolutely, all of those ones should say 2 on them. They all should say 1s2 on them. Yeah, they absolutely should. I don't know where that... Oops. Okay. All of them should definitely say 2 on them. That's just me not typing properly. Okay, so now let's look at sulfur again and look at where's the last full p orbital. Which p orbital is it? So we're looking and we see it here. We have the 2p6 is the last full orbital here. So this corresponds to the second row's, the end of the second row. What element is at the end of the second row? Yeah, so this is neon again. It's the same. It's only 3 elements past aluminum, so it's going to be very similar to what it was above. So we're going to write this one as neon, and then we have a 3s2 that covers the sodium and the magnesium, and then we need aluminum, silicon, phosphorus, and sulfur, so it's the 4th one across. So that's 3p4. So that gives us the core notation, or the shorter notation for writing sulfur's description. Okay, now we're getting to rubidium. Rubidium's getting really big. It's 37. I don't want to draw the configuration for all 37. As you can see, it's written here. It's pretty big. Where's the last full p orbital for rubidium? Which p orbital is that? The 4th one. So it's right here. So first we have to figure out what element is the 4p6, that one. So which one is 4p6? What are we starting with? Which noble gas are we starting with? This is going to be krypton. So this is the krypton one. So we put krypton here. And then how many extras do we have? It's actually really quick. It's 5s1. And that's all that's left. Now, the most annoying one is actually going to be this one, because krypton itself is a noble gas, and we can't just cheat and go krypton and say done. We have to say what's the one above krypton. We have to use argon for the one above krypton. So we have to go argon plus what's left. And so that's going to be this one, which is the 3p6 one there. And so then we're going to have to just put everything else that's written here. 4s2, 3d10, and 4p6. And now we're done. So that's my hint there. That looks good there. And we'll stop. So there's some notable exceptions because nature is just nature, and our descriptions of it don't make nature the way it is. They're just our best way of predicting and analyzing the way the universe exists. So we're going to do some notable exceptions. Chromium and copper have some exceptions. So what I want us to do for practice, let's write out chromium's core notation. So first we have to do is find chromium on the table. What number is chromium? Chromium's number 24, right? And so 24, it's in the middle of column 6 there. So we can just circle back. What's the noble gas that's before chromium? Argon. So we're going to write argon first. Argon. And then what's coming after argon? So argon's 18, so we're looking at 19. Well, the first 2 columns are going to be my S. So potassium and calcium are going to be my 4s2. So I get 4s2. And then I count across how many d orbitals am I going to get? 3d 4? 4. Okay, so 3d4 is what chromium is going to be. All right, let's do the same thing, but for copper. Does copper have the same, it's in the same row, right? Copper is in the same top row here, and so the starting point is going to be the same. There's just a different level of the d orbitals there. So we have argon, and then we have the 4s2 for my first 2 columns, and then our bottom ones is 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're 3d9 there. Okay, so what we're looking at here is this change here. So if I look at this one and I look at this one, what do they have in common? They're both not quite full, and that's kind of the thing. So D4, right, is 1 short of half. So it's 1 short of half full. D5 would be half full because the whole orbital is 10. And then 9 is also, so D9 is 1 short of full. So what we actually get is this trading of electrons. Remember, electrons can be in many orbitals. This is just generally their lowest state. But the lowest state for these two is a little different than just following the table. So what's actually going to happen is we're going to pull one of the S's and put it into the d orbital. So what we actually get for chromium is argon with a 4s1 and 3d5. So we actually get this weird thing here. So we get this 1 and 5. So there's still 6 electrons. It's still, all the electrons are there. We haven't lost any. We just moved 1. There used to be 2 in the first chunk and 4 in the second. So then we have we have 1 and 5 for chromium. Right? Okay. I understand it's definitely confusing. I understand that. But now I can see 2 different corresponding effects of this move. So now I can see S1 and D5 are both half full. Right? S can have a maximum of 2, right? It can be 1 or 2. That's how S works. And D is 10, so 5 is half full. So they're both half full. Instead of 1 being full and 1 short of half full, they trade, and so they're both half full. It's like an even-Steven kind of a maneuver here. So same idea here is we're going to do, copper is going to grab 1 from S and put it into the D as well. So copper is going to end up looking like argon and 4s1 and 3d10. So we get S1 is half, and D10 is full. So we get a half full and a full instead of a full and a like almost full, like 9/10 of full. And so that's where that's balanced out. So in chromium, we get a 2/2, and then the other one we get a half and a full. So what we're trying to learn here, and we can see from the chart from last class too, is that half-filled orbitals are especially stable. And so basically, getting to half full is really good for an atom stability. All full is good. That's classic. We're all full is good. That's why our noble gases are really stable. They're full of all of their shells. And so these are finding a more stable position to be in when they're half full. So if they fill a shell half full, that's really good for its stability. So if you're looking at this particular arrangement where you're like almost full and full, it's going to go, well, I'll grab one of those, and so I'm half full and full. So I now have half full and fully full. That's now a better, lower energy, stable arrangement. And then this one, 2/2 are also better. No one's close to being full. And these kinds of unstable things are what makes things more reactive. That was a whole lot of words, but hopefully this mostly made at least connective sense. A little? Maybe not. Okay. The next question is to, why does that matter at all? And that has to do with ions. So going on to how ions work, which is basically why we're doing all these electron configurations, is to show how an atom can become stable by gaining or losing electrons. And so this allows us to describe, especially that ugly middle chunk of all the d orbitals there, why some atoms can have more than one stable configuration. And so why they can have more than one charge, why they're multivalent. So quick recap, an ion is an atom that has gained, or to do it right way, lost or gained, because I think that's better grammar, lost or gained electrons. We remember from the last one, positives are called cations, and negatives are anions. And so negative ions add electrons, and positive ions take away electrons. Because remember, electrons are negative, so their plus and minuses are always reversed. So rules for negative ions, most stable, basically they just add electrons until they fill their more last subshell. They're very kind of straightforward and boring. They don't usually get multivalences. They tend to just be pretty strict. Okay, so let's do our two, because I got two elements here. Let's do their electron configurations to try to figure out how they can get there. Phosphorus is in the third row, element 15, so its lower noble gas is neon for 10. So we're going to put neon here. So we have neon plus what we have. So we're going to have 3s2 for my sodium and magnesiums, and then we count across, we have 3 of the next one. So 3p3, and that's phosphorus. That's 3p3 for phosphorus. Sulfur is right beside it, so it's very the same. We'll just put the same thing together. We'll put neon, 3s2, and then 3p4, just one more, because that's just, it's 16, it's one more past it. All right, so these things are short, right? So we have to add electrons at this last step. So we're adding electrons to make the last shell full. How many short is phosphorus to making a full shell? How many electrons do I have to add to this particular string so that it gets to be full. How many is full? 3, because I have 3 in my p orbital here. So this p orbital has 3 in it. I am 3 away from getting up to argon 18 full at the end. So we have to add 3 electrons to this thing. How many electrons do I have to add to sulfur? 2 electrons, right? So 2 electrons that way. So these 2 electrons show me what the ion is going to be. So this is going to lead to, oops, slide this back up to where it's supposed to look right, somewhere in here. So this leads to a phosphorus with a 3 minus charge because I have added 3 electrons to the phosphorus to make it charged. So to do the electron arrangement of this one, it's the 3s2, which is full, and now I have 3p6. I'm full, that last 3p6 is full. So now what if I look at sulfur? Very similar. What charge does the sulfur get? 2 minus, right? I added 2 electrons, it now has a 2 minus charge. So this becomes, sulfur with a 2 minus charge on the top. And its electron arrangement is going to be exactly the same. 3s2 and 3p6. So these have the same arrangement. So electronically, these are the same. Like they're outside, their electric arrangements are exactly the same. And so they have a fancy name for that. It's called isoelectric. So these 2 ions are isoelectric. In other words, they have the exact same number of electrons. They both have 18 electrons now. And so they are going to look on the outside the same as an argon, 18, full charged. All right. So that's how we basically create negative ions. And that's the whole thing. Negative ions are easy. Positive ions are a little more complicated because we get that middle D section of the periodic table, so there's a little more rules to deal with. So basically what we're doing for positive ions is we're taking away electrons. So we start to peel away electrons, and we peel them away in a certain order. The first ones we take are the p orbitals. Sulfur? It's sulfur 2 negative, not s orbitals. No. It's the sulfur 2 negative. And this is... Okay, first is the p shell, or subshell. So the first electrons we take away are from the p orbital. That's the first ones we take away. If we can take away some from the p orbital and make it full, or in this case empty, that's good and stable. The second we take away from the s orbital to see if those can get whatever, subshell. I should write them the same. Orbitals and subshell are the same names for things. I should erase this and make it the same. If you wrote orbital, you can leave it if you want. I should make the notes the same. Okay, so subshell. And then the last one is the d subshell. So I know I'm going to probably get, So this is the order that we have to take them away from. And so what we're going to do is we're going to try to figure out how we can best arrange these 2 electrons. So the first example we're going to try here is the SN, which is tin. So good news, core notation is available to us. Tin has 50 electrons. I don't want to write all 50 electrons out. So look on our table. What is the noble gas closest to tin, or lower than tin? It's krypton. So krypton is what we're going to start our tin setup with. So that's krypton. Oops, that's weird. I'm going to draw krypton. and then go on from krypton. So krypton's 36, we're going down to 37, which is 5s2. And I told everyone in the last class, this is weird. The one right beside it where Y, yttrium, and zirconium starts isn't the 5D. It's actually the 4D. That makes sense if you looked at the last lesson. 4D. How many? I use all of them because tin's on the 14th column. So I'm getting all 10 across there. So I get 4D10. And then how many of the 5p electrons do I have? Yeah, so hold up. We're now to 2 in this one. So to start making ions, which ones should I take first? First is these ones, right? So that's the first ones. So I'm going to get rid of those ones. If I get rid of those ones, I get a nice stable charge. So I can write this one as krypton, which is all of krypton, and 5s2 and 4d10. Everything's full, right? Because 2 electrons got taken away. I took those 2 off of it. Now I can also, it's also the next easiest ones to remove are the s orbitals. We don't like removing the d orbitals very much. We can do this one second, and so I can take both of those sets off. I can take 2 of the p orbitals off and 2 of the s orbitals, and that's a total of 4 away, which gives us our 4 plus charge on the tin. So this is going to be krypton and just 4d10. So this is the 2 different ways that you can get the 2 common tin charges. So if you look at the back of your periodic table, you can see tin has a common 2 plus charge or a 4 plus charge. And both of those are stable arrangements of tin in this case. So we're just going to remove both of them. Now, the next one, remember, don't forget, copper is the weird one. So its base isn't normal, right? So the base of carbon we wrote on the other page, it's an argon, and it's 4s1 3d10 as a base, because it's weird. It wants that 3d10 as a base because it's super stable. So for the first one, we can grab that s orbital is the first one to pull. So the first one to pull is definitely this one, and that gives us our 1 plus charge of copper. So this will give me argon and just 3d10. So that's the stable copper 1 arrangement. Now the next one is we can still pull charges off of this one. We can do this one next. We can take another one off that to make that charge here. So we can pull another one off of that one to make argon 3d9. And that's how we have to make our copper 2 plus. So it's a little more common and a little more stable for copper 1 to exist versus copper 2. But that's where that extra one comes from. And so now we can use these arrangements to try to predict what charges things will have without using just the chart of what's listed. This is where the chart comes from, where those common ions exist from. So we're going to try to predict the number of valence electrons based on given these core notations. So in this case, we're not creating them anymore. Just these are the notations. These are the electrons. How are we going to take them off? Which one of these ones from aluminum are we likely to take off first? So basically, the valence electrons are all the ones that not in the core, so not in the neon, so none of those count. All of those 10 don't count. Or anything D or F filled. Right? So if you filled D or filled F, those don't count. Everything else counts. So how many S and P orbitals do we have here? or how many electrons in the s and p orbitals is a better way to say that. 3. There's 3 electrons. 2, 1, 3. So there are 3 valence electrons. So if I look at gallium, I think that's called. Ga is gallium. It's number 31. We can look at which ones are we going to pull off of gallium. Which ones are the valence electrons in gallium? How many are those? It's 3 again, because I have just those and those. The other ones, no, we do not those. Not those, right? There, it's a full d orbital. That's solid. We're not going to pull anything off of that. So that's full and done. It's almost as good as the core. They're not being pulled off. So only the last 3 can. So this is 3 valence again. And I'd like to bring this up to you. If you look at the table, where are aluminum and gallium? They're right on top of each other, right? It's aluminum and then gallium right below it. Elements in the same column tend to have the same valence electrons. They're going to have the same. So if one has 3, the other one's going to have 3. They're very common up and down there. So let's look at lead. How many valence electrons does lead have? The F is full. That's full. We don't worry about that. And the D10 is also full. So it's everything left. What's everything left of lead? There's 4. Right? So there's 4 left for lead valence. And let's look at the last one, xenon. 410 is full. This is full. This is full. This one's boring. This is 0. It's a noble gas. It doesn't do valence electrons. It's full. It's all full. It's noble gas. So that is a whole lot for me to say, but I think it was not too much from Friday, but if you missed Friday, this would have been like, whew, lots of gibberish words at you. All right. I'm going to end this lesson here. There are questions there for you to try. Mostly it's getting valence electrons sorted and getting electron notations written into core form there.